Welcome everyone, I am Ruan Rajapaksha and today we are going to discuss Raychaudhuri equation applied to the pendulum problem. And I obtained this information from an excellent lecture given by Professor Sayan Kar, and I obtained from him his lecture, and I simplified it. And if you want the real thing, and I would ask you to check YouTube under Sayan Kar and Raychaudhuri equation, and you would see his lecture. But that for graduate level physics students, and he expects a lot of knowledge. Anyway, let's look what we are going to do today. Let's say we have a bunch of chickens running around. Now you cannot apply any equation to these because they're running around. There is no equation that they but if you have a situation like a pendulum, like you have two pendulums, right, and there's an equation for this pendulum moment, and it's given by d squared alpha over dt squared plus gol sine alpha, etc. Now let's say there are two pendulums, and let's say the relative velocity between the two pendulums from the center of gravity of to the other is u. This is the relative velocity, and the relative distance is x. Now we could use this equation, d squared alpha, and alpha is equal to L sine alpha, x is equal to L sine alpha, and y is equal to L cos alpha. For each one, you could find x and y at any given time. So you could find the relative velocity between these two pendulums at any given time based on this equation. It's all well determined. There's nothing indeterministic here. There are no chickens running around here. It's very deterministic. So u can be found because we have an equation for this one for x and y. We have an equation for this for x and y. So the relative velocity u and the relative distance x can be found for any given time. No problem. Now let's say partial u or partial x. The partial u is the relative velocity between the two pendulums. X is the relative distance from center to center, and partial u or partial x, change in u with relative to x. So we call that theta. I think original Raychaudhuri called it theta, so we're just going to keep that. And the change in partial u over partial x with time is d over dt. Change in partial u partial x is theta, so change in theta with time. So now let's look at the chain rule here. Df over dt equals, we just put dx and dx here. So it's df over dt, we just put dx here, it just cancels out. And dx over dt is u, change in x with relative to t, and df over dx remains. So now we go back to this equation here, d over dt partial u partial x, it's like the f here, and it's u times partial, d over dx, I just put partial over partial x. Now f is equal to partial u over partial x. Okay, f, so we just said df over dt equals dx over dt df over dx. Dx cancels out, df over dt, and dx over dt becomes u. And here instead of f, we are just going to put partial u over partial x. So the partial u over partial x, we get u times partial over partial x. D over dx, I just made it partial over partial x. F is partial u over partial x. So u partial squared u over partial x squared. Okay, now we have, let's leave it there. and we are going to find the equation for this. And let's look at this equation. This is a separate equation now. Partial of partial x, u partial u of partial x. First you take u out. When you have two functions, first you take u out, and then partial this one, partial squared u of partial x squared, and then you take partial u of partial x out, and then partial u of partial x. And so this one is equal to u partial squared u of partial x squared plus this. Okay. Now what we are going to do is, see this here, we are going to put, now here we could take this one here, we could take u partial squared u of partial x squared is equal to this minus this. Okay, we just take this to that side. Okay, so that's what we are going to do. So instead of this, we are going to apply this whole thing. So what we get is, come here, do dt partial u of partial x. Instead of this, we get this. Now instead of this here, we are going to put this portion here, partial of partial x, u partial u of partial x minus partial u squared of partial x squared. So we have this equation, and now partial over partial x, u is partial x over partial t, x over t, dx over dt, and then we could keep here, and then this stayed the same, and this would be, now what happened here, the partial of partial x equals, these two cancel out, and then you get partial u of partial t. So this is the equation, and d over dt partial u of partial x. This is the velocity, change in velocity in respect to time, so there is acceleration, so partial f of partial x minus partial u of partial x, and then we get theta partial u of partial x, and d over dt becomes theta here, we just put theta here, and then we get an equation like this. This theta is basically called the expansion or contraction. Expansion could be minus. Now remember, we said u and x for the pendulum problem can be found. What is u? U and x. This can be found with this. We have equations here. I didn't do it, but it can be done. So you put u and x in here, and to this equation, partial u partial x, you put the u that we got from there, and then you could simplify, and then you could have theta versus t graphs like that. So what we are going to find is that these theta is going to go to minus infinity, and think about it. What is theta now? Partial u of partial x, right? Now when they are going to crash, these pendulums are going to crash. When they're going to crash, x goes to 0. X goes to 0, and u, between these two pendulums, the u is the relative velocity, will be going to becoming decreasing. Will be decreasing. So it's going to be negative. So when they're about to clash, x is 0 almost, x is 0. So it's minus infinity. So that's what we are seeing here. So minus goes to minus infinity if at a finite time. So partial u of partial x or theta would go to minus infinity. Now, importance of this is that, let's say you have 4 projectiles, and these 4 projectiles are sent out to the air, and there are equations for these projectiles. Mg cos alpha sine alpha, whatever the v, that equation, and then you put those equations, and after time t, the projectiles would be something like this. Okay, so what happened here is an expansion. That would be theta And then also it could shear. Shear is something like that, move to the side, and also rotation. So all these can be found, basically. And you could apply the same idea for fluid mechanics. And if you take 4 fluid particles and they have flow lines, and then after time t, you could develop the flow lines, and then you would get something like that with expansion, shear, and rotation. So these are the basic ideas that we are going to apply in the next section for geodesics, Albert Einstein's theory of relativity. And that's exactly what Raychaudhuri did. And that's the interesting part. But this is basically a simple problem just to give an idea how it would work out for the geodesics. Thanks for listening.